Hello everyone! Yes, it's time for a bit more Python code, everyone's favorite. Don't lie, you know it is. But this time around, I wanted to actually demonstrate how the factor field can be generated in two different ways in code. So first, I've gone ahead and cleaned up a bit of the code that I had last time. I've created a function up here to actually generate the images that we'll be using, which will help save some space rather than having to repeat this multiple times. I've also created some variables here to describe the side length. And you'll notice that I've currently got it set to a side length of only 10. Now there's a reason for that, which I will get into in a little bit. But first, you can see that this is the important part of the original version of the code. So I explained this better in the previous video that was on the factor field, but just to briefly tell what's going on with this, this is going to be creating an array, which will be full of the number 1, and it's going to be a 10 by 10 array here because the size is going to be 10 by 10 up here, given this length. When this is run, the number 1 will be interpreted as a white pixel, and then the number 0, which we are updating certain values to 0 right here, those will indicate a black pixel on our image. And the way that this is done is that it goes through a column from 0 up to this side of the length, which is 10 again. So it goes from 0 to 10. And for the row, it starts with the column that we're on, and it goes up to the length because it's the same length down as it is across because it's a square. And then it skips by the number of the column we're on plus 1 each time. That will generate the column. And you can see this is called factorfield.png. When we look at it, it's this. So again, what this is the first column, it's every single one going down. The second one is every other one going down. Third is every third going down. The fourth is every fourth going down, etc. So that's how this is generated. That's the original version. Again, you can see the previous video to get a little more in depth on that, but that's this compact code that runs that. The alternate version of the graph now, as you can see, we've got this graph squared. And because we're squaring from a 0 indexed array, I'm adding 1 so that we get the right values. And you can see here the graph squared is simply this length times that length again. That's what a square is. And because of that, that's why this number is so small, because these will be giant very quickly. So in this case, we set this up. Our second graph is set up exactly the same way that this is started with. So we just fill this grid with 1s. Now we go through and we change cells to 0 based on these patterns instead of this one. So while it's a little more complicated, it's actually not that much more complicated. The biggest thing to bear in mind as we're going through this is that because, again, it's a 0 indexed array, we have to do some shifting before we do our math operations, and then we shift back. So I'm going to have to transpose, for lack of a better word, the row that we're using here, which I'm just calling X for now. It's actually not really a row or a column. This is just going up all the values. And we have to do our math functions by adding 1 to that, because when X is 0, we need to look at what 1 is and go through from there. Then when we're ready to plug it back in, then this 1 that we've added in, we have to take off. So that's what these -1s end up doing. So again, we shift over to do the math, get the right values, and then we plug it back into the array, shifting it back to the right spot. So that part's the only part that's kind of tricky with us. The math works without these plus or minus 1s. So if you're just looking at what the math is going on in this, we can ignore this X completely, and we can ignore all the -1s. So this is what is happening when we're going through these loops. And I'll start by just saying X equals 3, because if we start with X being 0, it's kind of boring, and it doesn't really explain a whole lot. So I'm going to start with 3 to explain the process, but it really does go through starting at 0 and goes up to that length, which is, again, the 10. So the first thing that happens is when x is 0, we convert it to 1. So when x is 3, it's going to be n equals 4. So then we start with this y going from 0 up to n. So that's 0 to 4. Now when y is 0, then what we've got here for our new row is we're going to multiply 4 minus 0 times 4 plus 0. That obviously is the same thing as 4 times 4. So this new row, when we start, is just going to give us the square. So 4, our new row is going to be 16. At row 16, again, for now, ignore these minus 1s. That's just telling it where to go in the array. Mathematically, the new row is 16, and we're saying that this value here, which is the 4 minus 0, that is a factor of 16. So 4 minus 0 is a factor of 16. 4 plus 0 is also a factor of 16. In this case, it happens to be the same number of 4. Then next time through this loop, then y will equal 1. So we're going to have our new row of being 4 minus 1, which is going to be 3, times 4 plus 1, which is 5. Well, 3 times 5 is 15. So row 15 is going to have 3 added here and then 5. So both 3 and 5 are put in as factors of 15. Now the y increases to 3, and we have 4 minus 3, which is 1, times 4 plus 3, which is 7. So now row 7 is going to have the values of 1 and 7. So 7 has factors 1 and 7, which obviously it does. But when you're thinking about this pattern, it's kind of a weird one, right? So you start with 4 being squared, giving us 16, and then you have 3 times 5 is 15, 2 times 6 is 12, 1 times 7 is 7. But while those might seem to be coming out a bit random to start with, it's actually just what I'm doing here is really no different than stating this well-known equation. N squared minus 1 is equal to n plus 1 times n minus 1. The only difference between that and the equation I'm actually using here is I'm actually using the more generalized version of that equation here, which is n squared minus a squared equals n plus a times n minus a. That's what we're really going into. 6 squared is 36, and 5 times 7 is 35. Now, 5 is 1 less than 6, and 7 is 1 more than 6. 35 is 1 squared less than 36. And next on that, it would be 4 times 8, which is 32. And 4 is 2 less than 6. 8 is 2 more than 6. 32 is 2 squared less than 36. So that pattern continues with your 3 times 9, which is 27, the 2 times 10 is 20, and 1 times 11, which gives you your 11 at the end. So these numbers will all show up from the squares in the factor field from this loop. In fact, you can always spot squares further down because they make this parabola shape on the factor field, which you see here, this kind of chevron looking thing here. That indicates where the squares are. But you can see that this is not the only parabola in the factor field. There's also this thing over here. What's that one doing? Well, that is where the second y loop comes into play here. So instead of the square where we get that chevron thing, we're looking at what I'm calling the near square. So a near square is when you're multiplying a number times 1 more or 1 less than that number. So I call that a near square because it's almost a square, but it's not quite. Let's go back to our loop here, and let's again think of when x is 3, so n is 4. So what does this one do? Well, the first thing that we're going to do is 4 minus 0 again, because it starts back again at 0. 4 minus 0 times 4. So that again is going to give us the 4 times 4 is 16. That gives us nothing new. But when y equals 1, we start generating new values. Then 4 minus 1 is 3, and 3 times 4 is 12. So now we're going to have row 12 with the factors of 3 and 4. You remember in this loop, 12 was formed from 2 and 6. So between these two, we've now got both 2, 3, 4, and 6. The only factors we're missing are 1 and 12. Where those come in, I will get to in a little bit. But let's get back to this loop again. So after y equals 1, we get to y equals 2. Now we got 4 minus 2, which is 2, times 4. That is 8. So we now have row 8 being represented by 2 and 4, which again, 2 and 4 are factors of 8. Finally, we have y equals 3, and we're going to have 4 minus 3, which is 1, times 4. That gives us our 1 times 4 representing factors of 4. So with both of these methods filling out cells in our array that we convert to an image, we are actually able to complete the factor field up to the length of the side. So just this same side length up here. The difference between this method and this method is that we're using squares to fill it in. So this graph will actually extend all the way down to 100 rows. In fact, just as I showed you, the original factor field looks like this, then this is what we will get by running those squares and the half squares here, which you can again see in isolation down here. This is a square, that's a half square, square, half square, etc. But the first 10 rows, which go to here, this part is exactly the same as what's here. In fact, you see down here what I did is I made a cropped graph. What the cropped graph does is it takes the data from the second graph only. It's not looking at this first graph. See, it's taking the second graph data, which is here, and it creates a new array that starts out empty. So there's absolutely nothing in this array. It starts out completely blank. It goes through this second graph, and every cell that matches in this range, it puts into this cropped graph data array. And it's ignoring all of the extra data after this 10 by 10 square. So when we get this cropped data and we put it out, we get this cropped second factor field, and that looks like this, which as you can see is exactly the same as the original factor field. We end up with one big problem with this is that this is going to generate extremely huge pictures. In fact, just to show you what will happen, if I switch this over to 100, save that and then run this and let it update. So it's generating these. Now it's complete, and we tell it to go ahead and update. So first of all, this now looks like this. We get the 100. The cropped looks exactly the same, just like we would expect it to. But this is too large to open because this is like it says here, it's 8,192 by 8,192. That's the biggest that it can go to. And we're looking at 10,000 by 10,000 because we're doing 100 times 100. It's 100 squared. The good news is that I can open this in a different program. Let me go ahead and try doing that now. So this is going to be the entire one here. If we open with Paint 3D, let this come up here, it's going to tell us that the image is too big, but they resized it. So we can hit OK on that. And now we'll have to zoom in a bit. Come up towards the top and scroll over to the side. And now you can see where this has started to fill in. And the only problem with this being so big is it's too easy to overshoot. But here you go. The first 100 are filled out completely. The problem is, of course, then we've got all of these extra squares as we go down. I'm not sure how much of this will show up. Hopefully the resolution of the video is well enough that you can see this. But this is what we end up with. And of course, this isn't perfect in Paint 3D because it did resize some stuff. So if you wanted to use this as mathematical proof of anything, it's not going to work. But that is what is generated by this code. So feel free to copy this, run your own Python, change the sides however you want to. I almost forgot this, but remember when I mentioned about 1 and 12, where does 1 and 12 come into play? What row do we start with so that we end with a result of 1 and 12 in our factor chain? Well, you saw how we generated it from this method. all we have to do is reverse engineer and find what would bring about the 1 and the 12. All we have to do to find that is we start moving in both sides. So I'll just type it in here really quick down here. So we start with 1 and 12 on one side. So bring these values together. So we get a 2 and 11. We get 3 and 10, 4 and 9, 5, 8, 6, and 7. There you go. Those are the near squares, 6 and 7. So 6 times 7 is 42. 42 is what will bring all of these. So you get factors of 1 and 12, 2 and 11, 3 and 10, etc. You have to actually do the math. So 12, row 12 has 1 and 12. Row 22 will have 2 and 11. Row 30, 3 and 10, and so on. Say the number 15. How would you find 15? Well, again, you start 1 and 15. Then that would become 2 and 14, 3 and 13, 4 and 12, 5, 11, 6, 10, 7, 9, 8, 8. So you got 8 squared. So 15 is then related to 8 squared. So think about this. So 15 goes to 8 squared, which is 64, but think of the 8 squared part. 12 is going to 6 times 7. So do you see the pattern there? So 12, what is half of 12? Half of 12 is 6. 6 times 7 is what gives us this result. So you take the even number, divide it by 2, and take that number times the number 1 larger than it. That is what's going to give you the factor chain. Then for odd numbers like 15, 15 is related to 8 squared. So what is 15 plus 1 divided by 2? There you go. So take your odd number, add 1 to it, divide it by 2, and square that. That is the number that will result in your odd number having the factors of 1 plus that odd number. So given those two statements, the general rule is for an even integer, divide the value in half, call it x, multiply x by x plus 1. For an odd integer, add 1, divide by 2, square that result. So again, 13, well, add 1 to 13, you get 14, divide by 2, you get 7, so 7 squared. There you go, it's that easy. And you can verify because 7 times 7 becomes 6 times 8, 5 times 9, 4 times 10, 3 times 11, 2 times 12, and 1 times 13. 1 times 13 gets you back to the 7 squared. 18 again, so divide by 2 to get 9, multiply 9 times 9 plus 1, which is 90. And again, all you have to do is think, 9 times 10 is 90, right? And then you get 8 times 11, 7 times 12, 6 times 13, 5 times 14, 4 times 15, 3 times 16, 2 times 17, and you're back to 1 times 18 again. So there you go. And honestly, it's those types of patterns, which is why I absolutely love number theory, finding those types of things. And with that, I hope you all do have a wonderful day.